Blackout is RIT Launch's first Level 3 high-powered rocket with a completely custom aero-structure and SRAD flight computer. In the team's history, we have mostly used commercial off-the-shelf parts to produce our rockets. However, this year, the team spent considerable effort to be able to manufacture as much of the rocket ourselves, in particular the airframe. Using three distinct methods of composite manufacturing, hand layup, winding, and molding, the team was able to produce unique and custom airframe components made of carbon fiber.
This year's nose cone includes a fully custom composite carbon fiber nose cone. The nose cone is 34.5 inches long, and carbon fiber was selected for high performance and to explore new composite manufacturing processes. The nose cone was first manufactured by making the molds. The molds were constructed by CNCing the negative geometry out of tooling board. The molds were then sealed and finished for the layup process. After the layup process, the two molds come together and a bladder is used to expand the inside. After the mold making process, the nose cone can then be removed from the mold and integrated with the rest of the rocket. This year's airframe consists of two 6-inch body tubes. The body tubes are custom filament wound using an X-winder machine and carbon fiber tow. The tubes consist of 3 layers following a 60, 90, and 60 degree wove pattern. These parameters were selected for the flight forces and pressures, and also to manage the manufacturing challenges with the tube winding process. This is the first year that the team has constructed custom tubes, and extensive experimentation was conducted in order to tune the process parameters. Initial tests were conducted at a 3-inch diameter and then scaled to the 6-inch mandrel. The filament winder uses a roll of 6,000 carbon fiber tow and wets the fiber through an epoxy bath. That fiber is then spun onto the aluminum mandrel. Once the 3 layers are complete and saturated with epoxy, a peel ply is applied to absorb any excess epoxy. Significant difficulty was originally experienced with the removal of the mandrel. Fortunately, the team was able to source liquid nitrogen to help remove the mandrel. The difference in the coefficient of thermal expansion between the aluminum of the mandrel and the carbon fiber allows for the shrinkage to enable easier removal. Any surface imperfections are then sanded smooth after the tube is removed, and a final coat of polyurethane spray is applied in order to create a smooth finish. The aft body tube is then used for the booster section, and it's integrated with a carbon fiber boat tail. The boat tail is manufactured through a traditional wet layup process. The truncated cone pattern that the boat tail is constructed off of is unfolded in order to prepare templates for the sheets of woven carbon fiber to be cut out of. The weave is placed over a plug which is designed to be left in the structure. That weave is then saturated with epoxy following a similar post-processing technique as the body tube.
So the fin can in our rocket in Blackout is located at the aft end of the airframe. It is composed of ABS, aluminum rectangles, and various fasteners. The job of the fin can is to provide structural integrity to the airframe of the fins. The fins are composed of carbon fiber sheets and milled into our desired geometries. And then each leading edge of the fins are filleted to provide more aerodynamic design. The fins are put into the rocket use of rocket epoxy and filleted with rocket epoxy. The fins themselves are CNC milled on a router. The design geometry was decided based on functionability and our desired altitude or apogee. And like I said, the fins are composed of pressed carbon fiber sheets.
For Blackout, we chose to use an M-Class 75mm 6-grain Cesaroni M2020 motor. This motor provided sufficient force to reach the required off-the-run velocity and the impulse to reach the targeted altitude of 10,000 feet. To secure the motor in the rocket, we made our own custom motor retainer consisting of 2 machined aluminum 6061 components, the thrust ring and a separate retainer piece. The ring is used to transfer load into the airframe, and the retainer piece prevents the motor from falling out. The ring was epoxied into place during the boat tail wrapping process, while the retaining piece was bolted on using 8 socket head cap screws.
The purpose of the recovery subsystem is to allow for the safe and complete recovery of the rocket. It consists of 2 standard COTS parachutes, a drogue and a main, which deploy at apogee and 1,200 feet by descent. Both parachutes are manufactured by the Rocket Man. The proper parachute sizes were found using the estimated weight of the rocket with all its constituent components. After manufacturing was nearly complete, the rocket was reweighed to confirm the accuracy of the calculations and allow for any changes to be made.
This year, the RIT Launch Initiative created a boilerplate-based payload with weight representation of 2 Genesee beers. The experiment of this payload was to test if Genesee beers fluctuated in temperature in all aspects of the flight, from the landing spot to the apogee and from the initial takeoff of the rocket. The structure of the payload bay is comprised of 2 plywood discs and 2 steel rectangles. The payload weighs approximately 8.8 pounds and houses our experimental payload, which is the Genesee beers.
The avionics bay is located in the upper tube of the rocket, and it is designed to be easily removed and inserted back into the tube. Each end has an aluminum bulkhead with a DB9 connector, which allows for avionics firings to pass through the entire bay. In order to ensure that our system will not be armed until the rocket is ready to launch, we have the deployment charges indirectly wired through 2 arming switches. Both are fixed into the airframe and are turned on from outside the rockets to ensure the safety of our engineers. Next to the switches is our 3D printed camera housing, which contains an Acaso EK7000 action camera. On the deployment side of the avionics bay, we have the 8-timer Quark with a SRAD logger perfect flight as redundancy. As for data collections, we have an SRAD board Spica, which was designed to obtain telemetry for the rocket as well as detect apogee. This allows us to obtain and view live flight data like altitude, temperature, pressure, and acceleration. For tracking purposes, a GPS module with an additional active antenna is used along with a backup tracking device, the Beeline GPS. Since the airframe is made of carbon fiber, which is an RF locking material, external antennas are mounted to the outside of the rocket for the 900 MHz receiver and the GPS.
Spica is our student-researched and developed custom flight computer. It is used for data collection, and when used with the ground system, streams telemetry live so we can monitor and track the rocket during flight. It has an ARM Cortex CPU and several sensors, including an inertial measurement unit, barometric altitude sensors, and a GPS. The data can be streamed live to the ground using a 900 MHz transmitter that is received by a second custom PCB on the ground. That second custom PCB on the ground takes the 900 MHz packets and converts them into standard network packets read by the ground software running on a standard PC. The ground software parses, logs, and displays telemetry packets received wirelessly from Spica during the flight. That telemetry data can then be viewed live in any web browser by anyone on the same network as the PC running that ground software. Spica and the ground receiver PCBs were both fully designed and programmed by our team, and fabrication of those boards were outsourced. All of the ground software was programmed by our team to run on any Linux-based platform.
Billy honk.
22nd, we successfully launched Blackout at IREC, reaching 10,234 feet, only 200 feet higher than our target altitude of 10,000 feet. We completed one of RIT Launch's most ambitious rockets. The team gained an impressive set of new skills and knowledge on the design and manufacturing of high-powered rockets, and we hope that this experience will lead the way to bigger and better rockets for the team. In the creation of Blackout, certain compromises were made to facilitate the completion of the rocket. Initial designs had us incorporating custom remove-before-flight switches and 4 custom cameras. However, with fewer active members and setbacks with the body tubes, we chose to use standard off-the-shelf parts rather than these custom creations.